Okay, so last time we started introducing the visitor pattern. Okay, as for every design pattern, let's understand what the problem is. And I would suggest later on when you practice this pattern here, I'll suggest some link of tutorial video for you to actually help you get some hands-on experience. But for visitor, I would suggest study that together with the composite pattern. They are quite closely related. Okay, let me just briefly brush up what you have learned last time quickly. Okay, we talk about this particular motivating problem. Okay, we're going to use that also for the visitor pattern illustration. We are trying to define a small expression language with only integer constant and also multiplication. Okay, addition. Sorry, and then of course each integer constant are considered as base cases, and also addition over here they are recursive cases, right? They help you build a tree. And then so this is the composite pattern that we have. All right, according to what we have learned. Any question about the composite pattern here? Okay, in general? Okay, we speak about many alternatives to actually do the composite pattern last time, so do review them. Okay, these are quite beneficial. Okay, and then we also talk about a new problem over here. Okay, composite seems to be working well. However, let's say we want to introduce more tasks for our application. Let's say for the small expression language which support integer constants and also addition, we somehow want to support different operations, right? What we talked about last time was we talked about things like evaluates, we got pretty printer, and also type check. You know, we got 4 or 5 different operations. It could be more in reality. And this is kind of our first design attempt, right? And we criticize on that using cohesion, basically. And by the way, if I simply say the following statements, I say, having this first design violates the single choice principle, right? As we explained last time, this is not right. So every time I say there's any design flaw, it doesn't have to be single choice principle, right? You have to judge, okay? So we talk about many design principles so far. Maybe later on for the exam review session, I can talk about more to review, but not now. But you should really review them. Okay, you should really see why cohesion is violated for this design here. I'll leave you to that. And now, single choice principle is violated and also is not violated, sorry, and also cohesion. So now let's talk about, also we talk about open-close principle, okay? Basically, open-close principle simply means for you as a developer, for your system, decide which part of your system should be open for changes and which part of your system should be closed to changes. You have to make that decision. Whatever decision you make, there's no right or wrong, but commit to it. That's open-close principle, okay? And specifically for this particular problem over here, remember we had a table. Let me show you the table very quickly. That's the table that we went over last time. You basically got 2 possibilities for this particular expression language, right? Either the structure of the language is open, or it could be that the operations is open, and the other one is closed, right? We'll talk about that. Also make sure you review that. And the final thing I mentioned was alternative number 2 is the precondition or prerequisite for visitor pattern, which means when you want to adopt a visitor pattern, it should be the case that you have decided the structure of your system should be closed. And also the operations that you want to support for the language should be open. But we're going to see exactly why. Okay, we just introduced the architecture for visitor last time. We're going to get more details. Okay, so that's basically visitor pattern. And then the visitor pattern, basically we're going to see a separation of concern. We got operations on one cluster, and language construct on another cluster. Okay, we'll go back to the diagram in just a moment. Okay, and then we're going to see open-close principle. And when you study this, make sure you understand why this is alternative number 2. Okay, we'll get there. Okay, so that's the diagram we started with. Hi, Jordan. So that's the diagram we started last time. And let's just go over very quickly, and then we'll go into details. Okay. Again, as I do encourage you to do, every time when you study a particular pattern, start with the architecture. Okay, it's really important. Okay, so now this is the diagram. I'll make it clean. Okay, I wouldn't go as much detail as last time because we went over that already. I want to point out several things to you. Number one, in order to extend your composite pattern to support visitor, you have to say accept over here. Okay, and then V over here statically is visitor. And then every concrete class, every effective class is going to make it effective for the accept. Okay, static type is simply visitor. We're going to see that dynamically, visitor can be many possibilities. Okay, and then there's a client-supplier relation over here. Make sure you understand why we have this particular label here for the accept. It is due to the visitor being here. Okay, you should really know how to draw client-supplier relation. Okay, it's really important. Now let's move the context to here. Okay, as I mentioned last time, so there are two things you have to remember when you want to create your own visitor architecture. It pretty much corresponds to the architecture of the structure on the left-hand side. Okay, let me point out to you again. Number one, each visit feature over here simply corresponds to each effective classes of the structure, right? For example, you got visit constant, also you got visit addition, right? They simply correspond to them. Okay, number one. Number two, the number of visitor descendants correspond to the number of operations you would like to support. For example, you have one descendant class called evaluator only for evaluation. You have another one for pretty printer just for pretty printing, let's say prefix notation. Also, you got a final one for type checker. Later on, if you want to add another operation, let's say generating IFO code or generating Java code, in that case, you have to add just one more descending class, right? Okay, and then one more thing to point out, okay? You can see at this level over here, you can see all the visit feature are simply deferred. So that means for any descending classes to be effective, they must implement, they must give some code. For example, you can compare this guy over here, visit addition, and also you got visit addition over here. And notice that they're both with plus. However, would their code be similar? No, exactly. Because the left-hand side, so the visit addition over here, that means you want to visit the addition for evaluation. And then over here is we're going to visit the addition for printing. Okay, different purposes. Okay, it's a very quick review of the architecture. Okay, any questions? Yes.
I just lost someone. Can you just explain the first and second point you bought, and like the why you just doing the the supply?
You mean the green arrow?
Yeah.
Sure. So the question was, you were basically concerned about this particular arrow over here, right? Yeah. This guy here. Sure. First of all, it's a client supplier. So we are saying that it should be pointing from clients to supplier. Okay? Why is that? You want to look at basically variable declaration. In this case, you can see that over here, we say accept is a feature that we define at this level. And then its parameter V is of type visitor. That means somehow we are trying to use the visitor features in the body of the implementation for accept, somehow. Right? That's implying that. So this visitor here tells me that visitor should be a supplier for us. Okay? Visitor, that means is a supplier. And then the expression where we declare that variable is the clients. That is why you have this arrow over here, right? If you point it the other way around, that's wrong. One moment, yeah. And then you put the name of the feature over here. Just say accept. Okay.
And just can you repeat what the point as the first point?
What do you mean the first point?
Whatever you described, the 3 points I think just before.
Whatever I decide. You mean for this client?
Thing, yeah.
Well, I don't necessarily remember what I said. Over here, so you can see this is a feature over here, right? Accept. And then for its parameter V, we're saying that we're going to use feature from the class visitor. That's why visitor is now a supplier. Okay, maybe that's what I said. Yeah. Mm-hmm. Good. Question?
Yeah, we have an inheritance type, and we have an effective class.
Mm-hmm.
We have subclasses that redefine features in the effective class.
Mm-hmm.
We just only need one client supplier error, right? If we're using, like, for example,
Oh, I see. What you're saying is this. In this case, you can see we are drawing, I'm going to talk about this case first, and then you can also refer to how we draw a client supplier for iterator pattern. Similar idea. The question was, you can see over here, we have this particular client supplier error over here because we got visitor over here, right? Let's say, for example, let's say over here, the constant over here is an effective class. That's itself, it also declares visitor. Do we actually have to draw another arrow over here to visitor? That may be more or less your question, right? Do you have to? Okay. And over here, I can also say accept. I would say it depends. Depends on what you want to show. Maybe somehow, for any reason, for the constant over here, for some reason you decide you want to have another feature called accept2, just for example, right? And then accept2 is going to take maybe E of type evaluator. So somehow you just want this particular specialized version for that visitor. And that, in that case, maybe it makes more sense to show this client supplier into evaluator. Okay. So what you really want to show in the diagram doesn't have to correspond to exactly what you program in the code. You only show a subset of that. It's called abstraction. Yeah. Mm-hmm. Okay, let me just undo this so I don't have to, so when you study the notes, you wouldn't get too messy. Guys, any question about the architecture before we see a little bit code? Okay, I would say the architecture for visitor is really important. We'll see something also similar when we talk about observer and state pattern, right? So you will see more and more examples, okay? Just make sure you get comfortable with the diagram. Let's now, before we go into implementing the visitor, let's see how we can use it. Using it first, before we try to implement it, okay? So now let's pretend we are the clients of visitor, okay? So now I'm going to show you this code over here, okay? Okay. Maybe I'll keep the diagram there so you can also look at that. So now we have a feature, test feature over here, test expression for evaluation. Let's say we have 3 variables over here. So we have at, we have C1, we have C2. Statically, expression, okay? Dynamically can be any descendant classes of expression. Also we got V, statically visitor. Dynamically can be evaluator, pretty printer, or type checker. So now, let's first of all think about what's going on over here. Number 4, number 5, number 6. What are we doing here conceptually? 4, 5, and 6. What are we doing? Oh, sorry, only 4 and 5. Beg your pardon. Number 4 and number 5. What are we doing here? Before I write it down. We are creating the expression tree, basically. So number 4 and number 5 correspond to how we build up the system for the equipment or furniture, right? You're building the tree. Okay, I'll write it down. So you're basically building the tree of expression. So that line number 6, we can create some visitor objects. Line number 6, because our purpose now is to evaluate this particular expression tree, that's our purpose. If we want to, let's say, pretty print the tree, we're going to create a pretty printer instead, right? Because now we want to do evaluation, okay? So now look at the most important line over here, okay? And then before we trace it, I want to show you first of all. This is how you typically use a visitor. You basically say, let me just write it down here, okay? So I can explain a bit further, okay? So when I say add dot accept, and then V. Okay, so now think about the add over here. This is basically the root. Hi. So can you fix that maybe later? I'm in a class right now. Thank you. Okay, so over here, so the add over here is the root of expression tree. Okay, that's the add. Okay, we're going to visualize this in just a moment. And then the V over here is basically the purpose of doing this particular visit. I'll write it down. So V over here is the operation we would like to perform. Okay, so these are the 2 things. So we got expression being the context objects, and we got the visitor being the arguments. What we have to figure out is exactly how this might work at the runtime. But before we see that, let's just see how we can use it. Magically, after calling this particular line, we can simply check the following. Okay, we can say that we just do a simple cast to say v, which is the visitor, v, which is the evaluator. Okay, you can see v over here. You can see statically v is static type is visitor, which doesn't change. And then if you look at that over here, we're trying to cast that into evaluator, which means we believe it is dynamically evaluator. I hope that's quite obvious to you because you can see from line number 6, we did create dynamically evaluator, right? So that's why we can cast it. And then one thing that's kind of missing from the diagram, I'm going to put it now. You can see over here, in our visitor architecture over here, this guy here, right? You can see we only support currently 2 features. We got visit constant, we got visit addition, right? Does it support the feature called value? It doesn't. So that simply means if you simply say v dot value, which represent the evaluation result, right? So this is not going to compile because value is simply not defined in this class over here, number 1. And number 2, where should it be defined? According to the cast over here, we're trying to cast that into evaluator. That means in the evaluator, there is a new feature called value. Okay, number 1, I'll let you think about it a little bit. What I'm trying to say is as follows. As far as the top level visitor is concerned, typically you only just put the visit features, visit constant, visit addition, that's it, typically. But now for individual operation, for individual visitor, because their result of visiting might be different. For example, in the case of evaluator, you would say, since I'm trying to visit my particular expression tree, I want to evaluate it. So the result should be some value. Agree? Maybe integer, let's say. So now value will just be integer. On the other hand, what could be the possible result from Pretty Printer? String, exactly. So what you can say is, I'll just say for example, it could be that this one here would just be, let's say result. Oh, actually say, let's say this. Let's say print result. And then string. And for type checker, it could be, let's say, Boolean. Just tell you either whether or not it's type correct, right? And then this will say type correct. And that will simply just be Boolean. Okay? So these are the visitor-specific feature you put for individual one. Okay? So they don't exist at the visitor level. That's why you might need a little bit cast. Okay? Of course, what you might argue was, if I simply say this, hypothetically, if you look at this line over here, what if I simply say v is of type evaluator? Well, I would say it depends, right? In this particular scenario, if I say v is of type evaluator, would it be okay if I say v.value? It would definitely be okay, right? But somehow v only got the flexibility to point to some evaluator object at the runtime. You kind of lose polymorphism. So I'll say that the balance is up to you. Okay, just realize why we're doing this cast over here. Okay, guys, let me just say one more thing before I take questions. We're almost done for this slide, and then we'll look at how to do this precisely. After doing this, what we will do is we'll simply say eval, which is a cast version, right, for evaluator, and say the value should be simply 3, because we are trying to build an expression tree with 1 and 2. Basically, we're doing 1 plus 2, and the result should be 3. Okay? Let me just highlight two things to summarize. In order for you to do visitor, step number 1, declare the visitor. Step number 2, build a tree for the composite. Number 2, right? Number 3, you want to somehow visit this particular tree by using accept. So the expression accept the visitor. Okay? And then after you have done the accept, you will simply just check the result for that particular visitor. Okay? So these are the typical steps you have to do. From line number 7 there, you don't see any recursion, do you? But the tree that we are building is somehow recursive. So it's interesting that even though line number 7 doesn't show any recursion, when you actually execute it at runtime, you will see some recursion. You will. Okay? Any question here just about what we have said so far? I deliberately don't talk about any implementation detail just yet. I just want to show you how you can use it to get some intuition. So you can also compare that with a diagram. Yes? Line number 6? What do you mean it will not work? No, so the one I put over there. So if you kept the original declaration over here, line number 6 is fine, because evaluator is a descending class of visitor, right? If you actually put hypothetically to declare V as evaluator, line number 6 will still be okay. You're just saying dynamically it's pointing to evaluator. What wouldn't work for this particular hypothetical declaration was if you say V, which is of type visitor here, if you say v.value, it wouldn't compile because value doesn't exist at the visitor level. But if you say V was declared to be evaluator, and then you say v.value, that would be fine. Okay? I'm just trying to point that out. Okay. Where you define the make feature for the visitor, I would say it's hard to give a general answer. I would say it depends on how you define your application. Maybe, yeah, one choice could be you simply say the make, as you pointed out. It could be that maybe the make in the visitor over here will just be deferred. It could be. And then in the individual visitor over here, you make it effective. Well, could be. I'm just saying that's one possibility. Or it could be that you have a general way to actually initialize all kinds of visitor so you can make it effective. It's completely up to you. That's why I didn't really show it over here because that kind of depends on the application. Right? But the most important thing to pay attention to are how to define the visit feature over there. Okay? That's the most important part. Guys, any questions? You okay? Okay. All right, let's see how we can implement the visitor. Okay, that's the interesting part. Okay. What I would do is, okay. How about we look at the slides quickly? Okay, I'll go over the code. You have a general idea, and then we'll look at details. Okay. So now, basically, we have the constant. The constant is directly inherits expression. Okay, and then we got the accept. And then this is the interesting bit. The way you implement the accept will be very standard, which means you don't have much freedom. Okay? This is what you say. Look at that line. We say, in order to define accept for constant, we simply say v, which is the argument visitor over there, dot visit constants, and then current. What's current? That's the constant, right? Current is like this in Java. Okay? So can anybody just imagine what this line is doing over here? Okay, when recursion actually comes, it may not be the root anymore. It may be a root of the subtree, right? Let me give you a little bit idea over here. Okay. This is saying the following. If I have, let's say, at was the root that we talk about. If I say at dot accept, and then I pass the visitor v, dynamically can be any of the descendant classes. What this tells me is, according to the definition I just showed, okay, I'm going to copy that over here. Okay, it's going to say v.visit constant current. Okay, or actually, you know what? I'll show you just another one here. Compare this. You can see the way we implement the accept over here, we simply say v.visit addition, and then current. Again, the similar pattern. All you got to make sure is if you are trying to define the accept for addition, you're going to say visit addition. If you're trying to define the visit for constant, you got to say visit constant. That's the only thing you have to be careful, because current is of a very specific type. Okay. Okay. Let me make myself a little bit clearer over here. Let me put this guy here. Okay. Before I talk about this particular one, let me just put this one here. Okay, let me say one more thing here, just to make sure you understand it. Let's say I got my class addition. And addition, of course, inherits expression, let's say. And we know that the expression class actually got the accept feature, right? So now what I will do is this. I'll just write it down exactly what you see over there. Accept v of type visitor. Now, pay attention to what I'm trying to write here. If I say v dot, oh, let me make it more valid. Do and n. If I say v dot visit constant over here, okay. Do you think this version will work?
No.
Would it compile even? Would this compile? I agree with you. It depends on what's being expected for the visit constant, right? But what's the type that's being expected by visit constant? Should be constant, right? Okay. Let's double check with that. Guys, this line is very important. Okay. Just make sure you understand what I'm trying to say here. I say v dot visit constant. Okay. What's visit constant? Go back to the diagram. If you go back there, you can see visit constant over here. The parameter is constant. So that means when you are defining your own inheritance hierarchy, you shouldn't put just expression over here. That's way too general. You want to put something specific enough. Okay? Okay? In that case, we'll go back here, and then we know that what's expecting is constant. Okay, as we said, right? Because you can see constant over here. And now, what are we passing over here? Addition. So now, is addition a subclass of constant? No. So you wouldn't compile, number one. So if I put this wrong implementation here in the exam, hopefully you will be able to spot it, right? It's a very easy application for the polymorphic feature parameter that we talked about before. Okay? Any question about this? I want to mention that first, okay, just in case. Okay, okay, so good. After this, let's now look at this particular guy here. I want to show you this one very quickly. Let me change the color of that. How about green? So now let's say we want to say add accept. I just want you to know what in turn it is going to say. What that would say is it's going to say v dot visit what? Addition. Exactly. Okay, look at that. You should match the type. Okay? Oops. So that would say visit addition, and then it's going to say current. What's current here? Give me a precise word to write out. Precisely. There's no addition here. Well, current is in the definition. But what would be the current right now? Current means the context objects, agree? What's the context objects? Add. That's exactly what I'm looking for. Okay. Interestingly, when you are calling add.accept v, in turn, it's going to call v.visit add. That's what I want to point out. I'm going to say a little bit more. I just want to show you first, okay, how you can apply the definition for the feature. There's something called double dispatch that you have to understand. I'll talk about it in detail. Don't worry, you'll see in the next slides. Okay. All right. So now let's go a little bit further. Let's go to iPad directly. Okay. So now this is a very easy exercise over here for you. From line number 4 to line number 5. Okay, sorry. Again, I make a slight typo here. Okay, how do you visualize that, right? How do you visualize line number 4 and line number 5, right? Because in order to trace the visitor, you should know how to really draw the tree. Can I assume everybody is comfortable with drawing the tree? Can I go directly to the tree? Would it be okay? Okay, I assume you're okay. If you are not okay, raise your hand. I'm going to draw that now. All right, then I'll draw it. Okay, let's do that quickly. Okay. Let's say this. Line number 4, we're basically creating a constant, right? We just say constant over here. And then every constant, if you remember, every constant is simply over here. Okay? Let's assume that every constant has some value, maybe integer. Okay? And then in that case, we're going to say the value for this particular constant is simply just 1. Okay? That's how you visualize that. Okay? Number 2, we are creating another constant. Oh, sorry. That one is called C1. Okay? So C1 is now pointing to this particular constant. And then the next one, we are creating C2 with value 2. You're creating a very similar object because they come from the same class. So that would be constant. The value would just be 2. So now, what about line number 5? We say add the make C1, C2. Somehow you can imagine that in the constructor make, we simply say left is assigned to parameter 1, which is C1, and right is assigned to parameter 2, which is C2. Right? Remember in the diagram over here, we actually got for the addition, which is descending class of composite, you got left and right. Okay? We can assume such constructor exists. Okay? Let me just finish that and then I'll take a question. And then over here, we'll have addition over here, and then we'll say C1 and C2. What it does is it's going to create, for example, C1 is now going to point to an addition object, right? That's dynamic type, addition. I'll say add. That one there has left, has right. And now the left should go to C1, and the right should go to C2. All right? So let me just say that the left should go to C1, and the right should go to C2. It's a very simple tree we are drawing. Yes?
Is exclude C1 pointing to that, or add that points to an addition object?
You mean line number 5?
No, in the diagram.
In the
C1 pointing to an addition object.
C1, no, C1 is actually pointing to, oh, maybe, I think I see what you mean. I just put the wrong name. Thank you. Absolutely. Add over here, right? So that should be add, of course. Okay, that's a tree we're building, right? That's a tree we're going to focus on to see how the visitor execution is going to happen, okay? That will be a little bit recursion we have to look at, okay? Because when you start from the top level with add, it is the composite recursive case. You have to go down to the base cases for C1 and C2. That's when you can return. But we're going to see that. Any other questions about this? Okay, that's how you visualize, okay? Let's assume we have the structure already. Much better drawn over here, okay? It's the same structure, the same. The only difference is I added another object over here, which is evaluator. Remember, in line number 6, we also say create evaluator and V, right? That's why you also see V over here, okay? So we got a tree, we got a visitor of type evaluator dynamically. Let's see how we can trace add.accept V. I put all the classes that you should know over here. Okay, let's go over them quickly. So that'll be the only example we're going to do for visitor. So let me know if you got any questions. Okay. Of course, when you actually do the actual projects, you actually need much more complicated tracing. But we'll start with the basics first. Okay. Let's go over the classes we need. First of all, let's talk about the expression side, right? So we got one expression descendants, which is constant. We got another expression descendants, which is addition. Addition got left and right. And then remember, both of them got accept over here. And then we simply say V dot, one is visit constant, the other one is visit addition. Put it correctly, right? On the left-hand side, we got the cluster, the classes from the cluster for visitors. We got class visitor here. We got visit constant. We got visit addition. Okay, they are deferred at that level. And then we got, let's talk about the evaluator here. So the evaluator over here is simply inherits the visitor. Okay, so we're talking about this class over here, if I might show you once more. We talk about this class here. okay, evaluator, which inherits from visitor. Let's see how we can define that. You can see we define some new attribute over here which does not exist in the visitor, just new attributes of type integer. Okay? And then we got two features over here. One is called visit constant. The other one is called visit addition. Okay? For the visit constant here, it's very straightforward. How do you evaluate a constant? It's trivial, right? Just return the value for the constant. So in that case, you simply say whatever value it is, which the client is going to use, will be assigned to c.value. Okay, that one's easy. So now, if you look at visit addition over here, that one's interesting. Okay, why don't you look at the code just before I try explaining to you? Okay, look at the code. It's not many lines. Look at this part here just for 30 seconds. And see what we're doing here. Okay. Can anybody try to explain to me what you have seen before I try to explain? Is there any recursion over here? It is certain recursion, kind of implicit. Not the classical recursion you saw in 2011 or 2030. That's okay, still recursion, right? But now, can anybody explain to me what's happening here? Especially, I'll give you a little bit hints. Start with the local variables. Why do we need those two local variables? I'll lead you a little bit. I started with, I want to visit this particular addition objects. Somehow, it's too complicated for me to do right away. So I have to delegate to some recursive call. So what I do is, somehow I want something to handle the left subtree over here. I want something else to handle the right subtree. How do I handle left subtree? I create another visitor. How do I handle the right subtree? Create another one. That's what's happening here. It's very similar to what you learned about recursion before, but slightly different way. Okay? What you learned from 2011 or 2030, how do I handle a tree in general? Let's say binary tree. If I start from the root, the tree is too complicated. I'm not reaching the base case yet. What I will do is I'll recursively call the left subtree. I'll recursively call the right subtree. That's what you learned. Similar here. Here I'm saying somehow the expression tree is too complicated for me to follow, to actually evaluate right away. I will simply try to see what the type of the root is, and then I will somehow get the left subtree and try to create another visitor object to visit that specifically and get its value. And then I'm going to visit the right subtree specifically using another visitor and get its value. And then I combine the values of the two local variables, visitors. Okay? Overall, that's what's happening. We're going to trace it. That's any questions so far? Okay, I'm just trying to go slowly, right? It's really important to get this right. Okay, and what we will do is we're going to trace this line specifically at the accept. And then we're going to describe a very important concept called double dispatch. Anybody heard about double dispatch before? Anyone? No, that's okay. Double dispatch simply means the following. Dynamic binding is going to happen twice. That's what it means. Okay? I'm going to lead you to observing this happening. Okay? Let's say this. I'll start with the feature call we are trying to trace. Okay, I'll start with that. If I say at dot accept and v. Okay, let's start with this. Should this line compile, first of all? Oh, if I just remind you very quickly, okay, it's not fair to ask you to memorize the code. So now, if I just remind you very quickly, if you look at the previous line, at was declared to be expression. V was declared to be visitor. Okay, is that good? Okay. At the accept, V, would it compile? It compiled because the static type for at was expression. Expression supports the accept. That's why it compiles. So now, dynamically, how many versions of accept do we have? How many versions? Is it just one version or different versions? I heard one. Well, if you recall this particular diagram over here, how many accept version do we have that's effective? One here and two here. Basically, for every effective expression class, you have one version of the accept. Agree? So now, if you go back here, so can we find out those two versions? So you can see when I try to do, I'll try to do a little bit highlighting here for you. So let me start with orange. When I look at this particular add, I know that there are two possible accept for me. Either this guy here, or it's this guy here. Which one? The first one or the second one? Why the second one? Yeah, which one to call depends on the dynamic type, right? What's the dynamic type for add over here? Addition, right? Because we know that add is dynamically pointing to an addition over here. So that means we're going to call the addition version over here. So I'm going to wipe this out. Oops. Right, are we okay? That's the first dispatch, first dynamic binding. Depending on the dynamic type for the expression, we're going to call the corresponding version for the accept. Okay? If you think you're so lost, ooh, that's not a good sign. You may want to either talk to your colleagues about catching up or talk to me. Okay? Anyway, the first one, okay, I'll write it down briefly. Okay, the first dispatch. Dispatch. Dynamic type of add is addition. Over here, so call accept from the addition class. Okay, that's the first dispatch. Let's see what's going to happen over here. Since we're going to call this particular version of the accept, okay, we're going to call that. And then you can see the V over here is going to replace the V over here, right? Okay? Oh, they happen to be the same name, but you can think about the V is this V over here. Okay? And then we say V dot visit addition current. So now, should this line compile? Why should this line compile? Compilation, I'm talking about. What's the static type of V? Visitor. Does visitor support visit addition? Yeah. According to the diagram of architecture, every visitor class support visit addition. Actually, support visit for every concrete elements in the expression. So compilation is not a problem. Okay? Compilation is fine. Now, how many versions of visit addition do we have? Why 3? Dynamic type, right? Dynamic types of the visitor. Okay, let me remind you. Okay, let me over here, so I will say pink. So we are trying to call this particular line over here specifically. And then if you look at the diagram again, okay? For the visitor, we got visit addition. And now visit addition might be defined in the context of evaluator, or maybe in the context of pretty printer, or in the context of type checker. 3 different versions, right? Now, the question will be, which version? Oh, okay, so let me just highlight it to you. Visit addition here, there are 2 possibilities I'll show. It could be the visit addition. Oh, yeah, actually, you know what? I already showed you the answer. Now, let me ask you a question. Okay, I should have put all the classes here. I should have. But anyway, let's look at the pink highlight again. Okay, let me rephrase my question a little bit. Okay, let's talk about this line here. We know that there are 3 possible visit addition there. 1 in evaluator, 1 in type checker, and 1 in pretty printer. Which version is it going to call? Evaluator? Not just because I'm showing that here, right? Yeah, yeah. Well, why? Okay. Dynamic type, okay? Just to remind you when you review the notes. Because when we say V of type visitor, dynamically it's evaluator. That's the reason. Okay? Please make sure you understand that. Okay? And then That's going to be the second dispatch. Second dispatch. Dynamic type of V is evaluator. Okay, so you're going to call the visit addition in evaluator. In that case, I'm going to highlight it. Question? Yes.
Like in the previous code, where we did create evaluator v.make, if we didn't cast it or if we didn't make it as a type evaluator, would we get a compile time error?
Yes, good question. A little bit side issue, but I can mention that quickly. Yes, the question was as follows. Let me just put it aside. Let's say we have V of type visitor. If I simply say creates v.make, that's what you're saying, right? Good. Guys, should this compile? I heard no. Why is that no? Visitor is defer. In Java terms, abstract. So you cannot create instance out of the abstract class. More precisely, remember what I said before. When you actually don't put any curly brackets over here for creation, then implicitly you want the dynamic type to be the same as the static type. So this is as if you try to say creates visitor and then v.make is as if. So of course this should not compile because visitor is deferred. So you cannot use that as a dynamic type. Defer means there's some code missing. So at the runtime, you just cannot be a dynamic type. Just an aside. That's good. I'm glad you mentioned that. Okay, so now we talk about two dispatches, right? We got first dispatch and second dispatch. Basically, two dynamic binding takes place. And then we are landing ourselves over here. Visit addition here, okay? Let's continue with the tracing. We're almost done, almost there. When we say visit addition over here, apparently, you can see over here, the current, when we started our call, we say add.accept. That means the current for the expression is add. Agree? So that means the current over here is simply just add. Okay, I'm talking about this add over here. And then, so that means the A over here is simply talking about add. Okay, let's make it clear. And then we simply create two local variables. Okay, we got eval left, eval right. Think about one evaluator for the left subtree, another evaluator for the right subtree. Doesn't matter how complicated they are. Okay. So now what I would do is I would say eval left, EL. Okay, it's now going to point to another evaluator objects with value. In the beginning, it's simply 0, okay, to begin with. And then eval right is just going to be another ER, evaluator right. It's pointing to just another evaluator objects, and then the value will just by default 0. That's how we begin with, okay? Now, let's look at the very important two lines. That's basically how you do recursion. You call the left subtree recursively, get some result. Call the right subtree recursively, get some result. Combine them together, okay? Let's see. Number one, let's look at this guy here. So we look at a.left.accept, eval left. And it would be an exercise for you to see. You can see we are doing another accept over here, right? Do we have another instance of double dispatch? You see, every time you're trying to invoke the accept feature, that means you're using the visitor at some particular level of the expression tree. Every time you say accept, you're really invoking double dispatch again. Exercise for you. I'll write it down, the exercise for you. Okay, but I'm going to do that and then I'll trace the code just by giving you the result. Exercise, okay. Explain the double dispatch over here. Double dispatch here. Okay, I'll leave that to you as an exercise.
Can you repeat the one more time? So how does that work?
Oh, yeah, you're right. I guess I just running out of space. I should have said create eval left dot make. Maybe that's what your concern is, right? Yeah, sure. Yeah. So yeah, that's absolutely all right. So the concern was if I didn't even initialize eval left, how can I call that, right? True. What I should have said would be I would say create eval left dot make. I'm just running out of space. That's why you should put that in your code. Just illustrating concept over here. Okay, exercise for you. Explain how the double dispatch work in this guy here. Okay. Do you want some hints? Okay, sure. Okay. What's the context object for accept? Either left? Yes, Chelsea. Yeah, exactly. So this is my hint to you. Okay, think about it. Okay, basically, a dot left or a dot left over here. What's the dynamic type? That's the context objects. And then think about eval left over here. What's the dynamic type? Think about it. Okay. Now, this exercise is important. So either you do it now or you do it in the exam. Either way. That's what I usually say to students, right? I want to encourage you to do it. Okay. If you really got trouble, speak to me. Okay. We still got time before the exam. Okay, so what this will do is eval left over here is going to visit this particular left, right? Particularly. That one is actually very easy because you're already reaching the base case. It will just tell you 1. Because it will simply, eventually, when you try to do this exercise over here, your conclusion would be we are actually going to execute the visit constant specifically at the end of the second dispatch. So that means we are trying to look at the constant over here, the left subtree, and then look at its result. What's its value? 1. And then we will set the value of that one to the visitor. That means evaluate left is going to get 1. There's a little bit gap here, I understand that, but it is really important for you to complete the exercise over there to see what the double dispatch is. At the end of that, your conclusion should be at the end of executing this particular line, you end up executing visit constants over here at the second dispatch. And then that one there, the constant over here is going to be the left subtree of the expression that we talked about initially. Okay, and that one will just give you 1. Okay. Now let's do one more thing. Similarly, there will be another exercise for you to think about what will be the double dispatch for this guy here, right? Similarly, right? You can see for a single example like a add.accept v, we got 3 instantiations of the double dispatch, okay? And your conclusion from the green one over here should be that the conclusion for this guy here, a.right, accept. Eventually, we should also call visit constant again. On which one? The right subtree over here. And then that one is going to set the value of this particular simple right subtree, very simple, right? Just base case right away. And that one there is going to, so this is evaluated right, and change its value to be 2. We are not done yet. We are still, still the last line remains over there. So the last line is saying that for the current visitor value, because implicitly it's like a current value, like a this value in Java, right? The value over here refers to the value of the current visitor, like a v over here. Because in order to evaluate this original line, we have to create 2 local eval left and eval right. But once we have done that, now we have to combine their results so that we can know the result for this particular evaluator. Okay? So now, what's eval left value? 1. And what's eval right value? 2. 1 plus 2 will be 3. So that means we put 3 over here. So when the client actually, after they call accept v. For the client, from the client's point of view, after calling this, even though it was such complicated local visitor going on over here, that's okay. From the client's point of view, after calling this, when they say v dot value, eventually what they will get is 3. That's all they know. You can see even for the simple case, it's kind of sophisticated, but that's the beauty for the visitor pattern. Because now we actually achieve cohesion, right? We got complete separation of concern. Question?
So for the line 8 dot left out of 7, 8 dot left.
Which line? Sorry, say that again.
The first line of the do.
Sure, no problem. Let me focus on that, and then I'll take your question. Yes. So you're basically asking about a dot left, the set eval left. Okay, what about it?
So double dispatch occurs. So the first dispatch occurs in the 8 dot left.
Correct, because a dot left is of type constant. So that means you're going to call the version of accept in the constant. Okay, yes, and then?
Okay, and then where's the second dispatch?
Second dispatch depends on the dynamic type for the arguments, which is eval left. What's the dynamic type for eval left? Dynamic type for eval left. Well, what's the dynamic type for eval, what's the dynamic type for eval left? Well, that's kind of missing from here. Well, I said I should have put it, right? Eval left, it should be evaluator, basically. Well, you should have created that, yeah. So that's the second dispatch. So that means we're going to call the visit constants in the evaluator class. All right. Question, yes?
We have more structured composites. Would there be multiple dispatches, or is it still
Okay. The question was, let me just make it a little bit, I like the question. Okay, guys, assuming that you're reasonably okay, I wouldn't expect 100% comprehension. That's not possible, right? This is maybe the 5th time teaching this. That's why I can say more smoothly. When I was learning this in 3311, 15 years ago, I didn't quite get it. Oh, maybe, how many years ago? 2005 winter. Almost 14. Yeah. So I wouldn't blame you too much, if you didn't quite get it. But take some time. As long as you get it before the exam, I'll be happy. Okay? Huh? Yeah, I've been using iPhone, yeah. Somehow I improved the example a little bit, so you have a little bit more visual, etc. Yeah. Anyway. All right, back to your question. I think that it's a very good question. I think that will help your project as well. Okay. Let's say this. Your question was, let's say we made a composite a little bit more complicated, a little bit. Okay. Let's say we got our expression over here. I'll say expression class. Okay. Under which, let's say we still got a constant. Okay. Effective. Okay. Let me say this. Let's say I got binary operation. I can even make it effective if I wish. Okay, binary operation under which I have, let's say, numerical operation, and I got, let's say, addition, and then I got subtraction. Let's say, of course, it can be as complicated as you wish. So now let's say this. If I have something like this. E of type expression. Okay, and then I say creates. Let me use subtraction for example. Okay, dynamically, I say subtraction, and then I'll simply say of E dot make. Okay, and then let's say I got another, let's say evaluator for example, and then I'll simply say evaluator. Okay, let's say I do a little bit code over here to build a tree. Let's say I'm gonna omit that part. I'm gonna build a tree for subtraction. Right? It could be something like this. For example, I can build something like 2 minus 3 minus 4 minus 4. Right? It's a complicated one. Apparently, there will be a tree for this. One exam question could be, I give you this hierarchy for free. However, I would say now build a tree that correspond to 2 minus 3 minus 4 minus 4. Think about it, okay? Okay, so now, let's say we built a tree already, and what I will do now is, let's say I also created, let me also create it. I can say creates e.make. Okay, I'm just creating an evaluator, okay? Oh, I'm so sorry. I meant to say eval.make. Okay, let's say now I talk about one line here. If I say e.accept, and then I would say eval. That's kind of what you're asking, I guess, okay? How is double dispatch going to occur over here? Chelsea. Okay, but is dynamic type for E quite obvious here? Is it fixed? Yeah, it is, right? Because we only built in the tree in the dot 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 part. So if you look at that, E over here, dynamic type is simply just subtraction, right? So the first dispatch tells me that dynamic type of E is subtraction. So that means I'm going to call the accept over here only. So usually, as soon as you commit to the specific dynamic type, it's guaranteed it's going to call that version. Yeah. It's a long answer to your short question, but I think it's worth talking about it. Okay, by the way, what's the second dispatch then? Just by the way. Yeah, so somehow you want to know what's the dynamic type for eval, right? So you can know which visit subtraction will call. Okay, I'll write it down, think about it. You definitely need some time. Second dispatch is going to be dynamic type of eval over here is evaluator, because we're trying to do that, so that's evaluator, right? Okay, which tells which version of what feature? Visit addition? Visit subtraction, right? It's guaranteed for every concrete class in the expression hierarchy, we will have a corresponding visit feature. It's guaranteed, right? If you follow the pattern faithfully of visit subtraction feature, okay, to be called. All right, question, yes.
Like for this example, as long as the dynamic type of V is evaluator, will the second dynamic type or the second
Yeah, so yeah, exactly. So here, the visitor we are passing, I'm just making it a little bit simpler. I just say eval. The static type is simply already evaluator. That leaves you very little flexibility of what its dynamic type should be. But typically, you should really put some V of type visitor. So you got some flexibility about polymorphism there. But what's going to happen at the runtime still depends on dynamic type, for sure.
And so if I'm understanding correctly, the evaluator class basically will either return a constant or it'll recursively call another evaluation.
Right. For the evaluator, what does it really return? Okay, don't lose the big picture. If you look at this particular class over here, we got evaluator, which inherits from visitor. We're only introducing a new attribute here, value of type integer. So that means it doesn't matter if you visit constants, or you visit subtraction, or you visit multiplication, whatever. Eventually always return some value. Yes. Okay? Let's take some time. We can review this later, but any questions? Yes.
Sorry, just a small detail about the diagram that you had on this next slide. I just wanted to understand how often it was deferred.
Which one? Yeah, I would say whether to make this class either effective or defer is completely up to you. If you don't want any user to create dynamic type of type numerical operation, you should make it defer. Or you can make it effective. It's completely up to you. Yeah. Yeah. Not necessarily. The question, Michael's question was good. Should the leaves of the inheritance tree be effective? Yes. Should the internal nodes of the tree be defer always? Not necessarily. Because remember, inheritance is for you to share the code. Sometimes maybe for a particular intermediate ancestor class, you just contain all the code over there. It's just not deferred. Yeah. All right. Okay, guys, I think for visitor, one more thing to talk about, okay? Design choice. Okay, everything in the slide has been discussed already, okay? Everything, nothing missed. Okay, there's an example we went through, double dispatch, okay, you can look at that. And then, now the final slide is about when to use the visitor pattern, okay? So now, what we want to see is, if you got a visitor architecture already, you want to know whether my system is really suitable for that. For that, you have to refer to open-close principle a little bit, okay? According to open-close principle, you should have already committed whether the structure should be opened or the operation should be open, either way, not both. You shouldn't make your whole system open. That doesn't make sense. You shouldn't make it both parts closed either. That's useless. Nobody can use it. What's the point, right? Okay, let me talk to you about this idea here. You can read the slides, don't worry. I will just talk about the idea here. Okay, so now I got several questions over there for you. Okay, we'll answer them gradually, don't worry, okay? Let's again go back to this clean architecture for our visitor pattern, okay? So now let's answer the question one by one, okay? I kind of put it in a logical order, okay? Question number one. Let's say, what if, let's say we have already done constant and addition, we have done evaluator, pretty printer, type checker, we have done everything, okay, it's working. Always, the way for you to reflect about your design is to think about extension, okay? Question number one. What if there's a new language construct to be introduced? For example, I want to introduce, let's say, modulo. Which cluster should I change? Expression only? I heard both, okay? Let's see how, okay? Let's say over here, let's say I want to introduce a class called modulo, okay? How do I change the expression language part? Add a new class, agree? Okay, what I will do is I'm gonna add a new class over here, and then I'm gonna call that modulo. And then for the accept, I can just do whatever we said before, right? You would say v dot accept, v dot visit modulo, and then current, right? That's what you would say. I'm gonna omit that part, okay? Accept. Is that the only change? Okay, do you agree there will be more changes? In that case, are we adding more than one places? If so, what principle are we violating? Single choice principle. Please don't say single-then pattern again. Okay, single choice principle. Oh yeah, they're very different. Yeah, please make sure you know it. Yeah, yes. If you don't know, you can talk to me after class. Okay, single choice principle, single-then pattern, they are very different, even though they both have single, right? Very different. Okay. Okay, now second change. We have to make sure in the visitor class we have this introduce visit modulo. And then over here, what should be the parameter type? Modulo, thank you. And modulo. Okay, over here, and then anything else? Oh, should it be defer or effective? Defer. And now, anything else to add? Just one class or every class? You can see now the modulo, visit modulo being deferred, it will be inherited to every descending class of the visitor. In order for those classes not to be deferred, implement them, okay? If you got 100 different operations, 100 different operations to implement, right? So now what I will do, I will write it for completeness. That means you're gonna say visit modulo, okay, something here, that'll be effective, okay? Also you're gonna say visit modulo, and then something here, also effective, implementing different way. And visit modulo, and also something here, effective, right? 1, 2, 3, 4, 5. 5 places. Not good, okay? Questions?
Sorry for interrupting, but if you establish that we're violating single choice principle, we're still continuing with the design, right? Okay, I understand that.
Well, I would say if you only do this introduction of new language construct only rarely, I would say that's fine. If you do it too often, That means you shouldn't use a visitor pattern.
Does module also inherit from expression?
Oh yeah, because yes, there's something I didn't. Oh yeah, yeah, absolutely. Michael, you got a very good point. Absolutely, I forgot about multiple inheritance. Yes, thank you for correctness. Absolutely, yes. Okay, that's the first question. So that means in the case of visitor pattern, the prerequisite is the structure part should be closed. If you're breaking the closed part, you're going to violate single choice principle. Okay, that's the point. Okay, and now let's answer the second question. What if I'm trying to do a different kind of extension? What if, let me use green. What if over here, a new language operation is added? Let's say I want to generate C code for optimization, let's say. How many places to add? Just one place? Are you sure?
Yes.
Good. Yes. Are you Yeah, well, for example, one operation is evaluator, one is pretty printer, and the other one type checker. I might want to do more. Okay, Michael is exactly right. So if I want to introduce a new language operation here, what I will do is, I'm running out of space, but if you can just let me draw it over here, it's an inheritance, okay? I will simply put, let's say, C code generator. And now, what should I do inside this particular new operation class? Yeah, if you think about it conceptually, it makes sense. Since I'm defining this particular operation for generating C code, I should define how that should visit every effective components of the expression tree. Okay? So that means in a single place, like a single class, right? I'm going to define visit constant and also visit addition. And also, for example, visit modulo if it's already there, right? Effective. So now, single choice principle is preserved because it's a single class I'm trying to do, right? A single place, single choice principle. So you can see the red changes are considered as bad changes for your visitor pattern. If you only do that very, very rarely, that's fine. It's acceptable. But your structure should be reasonably closed. On the other hand, the green changes, assuming that your language structure is very stable, you can add as many operations as you like as time goes by. Okay? Guys, any question about these two? Yeah.
What do you mean by generating C code? So when you generate the C code,
Oh,
you get that.
what do I mean by generating C code? You will see that in the projects. Yeah. You will see something similar in the project. Well, what I mean was, for example, let's say in your language operation, if you say, if I say, well, this is very trivial, right? If I say 3 plus 4, how do you, so this is more like a mathematical expression. How do you write that in C code? Just 3 plus 4. That's a trivial case. On the other hand, let's say somehow my expression language is so rich. Let's say if I got an object call, let's say object1 dot m1 dot m2. How do I generate C code for this? What kind of structure can you use in C code? You learn about struct, exactly. I gave you hints already. Structure, struct, right? I'm not sure if you noticed that. Yeah, anyway. Yes? We'll see. We'll see. That's not my concern. Yeah. My concern is which one can practice your skills the most, not really what you have learned. Okay. All right, guys. 2 more questions before we finish the visitor pattern. Okay, 2 more questions. Yes.
So like, we're talking about like a language construct, basically talking about like building the actual tree and the structure of your program.
Yes.
And the operations, like what
Yeah.
you can do with the.
Yeah. So you can think about for the visitor pattern in general. You actually got 2 clusters. The left-hand side is all about structure, how to structure the tree. The right-hand side is about the operation you can perform on the tree, right? Yeah. For language, it's just one example, right? Yeah. Okay, so 2 more questions over here for you to really reinforce the understanding. Okay, so now actually, I pretty much said that already, but I'm hoping that you can confirm with me. Question number 1. If the visitor pattern is already adopted, So what should be open? Operation should be open, right? Okay, so now if I ask you this question here in the exam, please try to explain that. Why operation should be open, but not the structure? Because if the structure was open, so that means you're going to violate single choice principle, right? As we just explained. Okay? Similar idea, if you actually got over here, if the visitor pattern is adopted, what should be closed? Structure, right? Because if you didn't make it closed, you're going to violate single choice principle. Okay?
In general, is it not so like one end or the other? It's more like a gradient of how you should use it. Like for example, in the visitor design pattern, you said it's okay to still add a construct as long as you're not doing it often. So does that apply to all design patterns?
You know, I would say, of course, usually in the school, we try to give you the principle, right? The principle works in general. But when you are working on your specific application, you have to have a little bit of flexibility and creativity. You might simply adapt the visitor pattern a little bit so that you kind of allowed some new construct to be introduced at some point, right? I'm just saying be flexible when you graduate, okay? Yeah, you don't have to say, wow, simply because I'm going to add just this single operation just for once, I'm going to abandon the visitor pattern, right? That's a little bit too extreme. Yeah. Okay. Guys, any questions about visitor? No? Are you sure? That's the last chance to ask me during the lecture time. You can ask me during office hour. That's fine. Okay. Question? Oh, interesting. To use visitor pattern to introduce error handling. So you're considering error handling as a operation. Yeah. Okay, guys, the question was, can you, for example, for lab 3, maybe a little bit too late. Let's say for lab 4 or future all your projects, can you apply the visitor pattern for error handling? Okay, that's the question. Depends. When you may consider using it, if the targets of the error handling, let's say the model you're trying to apply the error handling to, it itself is a composite. And also the structure of that doesn't change often. Then you can use that as a visitor pattern. That's my response to it. It's an interesting thought, actually. Interesting. Good. Okay, okay, if you no more question, I'll just take maybe 4 minutes, maybe 2 minutes. Okay, 2 minutes, 3 minutes. Okay. I want to talk a little bit about math models. Just give you a little bit idea. Okay, so we can start. We don't have to worry about the introduction on Tuesday. Okay. For the math models, we're gonna see that exactly why you want to use it. Okay, and then one more thing to say about visitor pattern. So if you go to the end of the lecture, okay, there was a tutorial video there which show you how you can implement the example that we talk about in class step by step in iPhone Studio. So check it out. Okay, tutorial video for composite and visitor. Okay, so about math models, before we do that, again, we do a motivating problem. Try to solve the problem, and then we can see how math model can help. So now, remember we talk about complete post conditions, right, before the reading week, right? We say that in the post condition, you should really try to address for every attributes, right? And say, how should you relate the pre-state and post-states? That's what we talk about, okay? And especially, what about composite valued attributes? Let's say the attribute I want to modify is an array. What should I say about the attributes? Let's say there's an array. And I only want to modify one particular slot of the array. How should I phrase the post condition? Implies, I agree. So how many cases should I discuss? Which two?
The ones that you're changing and all of those you're not changing.
Yeah, exactly. If I want to only change position I should be changed. The rest of the array should not be changed, right? Two things. Okay, I want to make sure you're comfortable with that. If you don't feel comfortable, you may want to review it before Tuesday. Okay, exactly what we said. And now we're going to do this using a stack. I'm pretty sure you implemented a stack, right, in 2011 or even 2030. Okay, I'll talk about very quickly, 1 minute, and then we are done. Okay. We are going to talk about 3 possible implementation strategies for the stack. 3 possible. Okay. Let's say we want to use array and linked list. Okay, Just 3 possible, right? We give the supplier as much freedom as possible, right? And by the way, implementation strategy, should it be open or closed? Should it be open to the public or should it be closed to the public? Closed, right? The client need not know what you want to implement the stack about, okay? I'll do this very quickly. It's a table. Basically summarize how you can implement it. So now, in order to know the count for the stack, we can simply get a count for the array or the linked list. Now, what possibility do we have to see the top of the stack? Basically, it might be the beginning of the array, or it might be the end of the array, right? Or beginning of the list, or the end of the list. Let's say we have that, okay? So we're going to consider 3 possibilities here. Let's say, in the case of the array, we say that the top tells us it's at the end of the array. That's why I say imp.count. In the case of the linked list, strategy number 2, we say it should be the first element in the list, first node of the list. And the third one is saying the last node of the list. How about push? How do we implement correspondingly? Strategy number 1, what should we do? Force, right? Force to the end. Strategy number 2, we simply somehow you can put the first. Okay, I'll show you the feature. And for the last one, extend. Exactly right. Okay. Okay. There's something called put front that might be useful to you later. And then what about the pop? Similar. So now for strategy number 1, you should really remove the tail. There's something called remove tail. You can remove the last elements in the array. And also for strategy number 2, you can remove the first one. You can go to the start of the list and then remove it, right? Okay, I'll just show you here. For strategy number 2, I can go to the start of the list and remove it. Or number 3, I can go to the end of the list and remove it. Okay, one question for you to think about. Imagine you're going to create 3 stack classes, 1, 2, and 3. Are their post conditions going to look identical or different? Okay, think about it. Okay, we'll continue from here for next week. Okay, I'll see you Tuesday.